Okay, so we're doing PWM signals for today. So PWM stands for pulse width modulation. Okay, so let's just type it down. Pulse width modulation. Okay. Pulse width modulation is actually um, a signaling system that has been around since 1846. So if you look at the history of PWM signals, the original pulse width modulation is actually applied to steam engines to regulate or to help regulate the speed of uh, locomotive trains. Okay. But the electronic version of a PWM signal was created in 1946 when they were trying to place in a encoding system towards a optical disc. Okay. So I think Philips, the US company Philips has a patent that is useful or is used in order to facilitate PWM signals. Okay. But again, a patent only lasts, I think, 50 years. So basically in 1996, and the patent for that one expired. Okay. So this is a PWM signal. Now, let's break it down into uh, what forms a PWM signal in this case. So when we look at this signal that we have here, we see that one block is actually 5 milliseconds, okay, or one horizontal time division. So meaning to say this is 5 milliseconds and this is another 5. And we basically have 10 milliseconds as a total period for this signal. Okay. So when we look at the period that's on or turned on, that's 5 milliseconds divided by 10 milliseconds, which is total period. We get a 50% duty cycle or 0.5 duty cycle. Okay. So PWM signals are always listed as values which focus more on the duty cycle. So if you have a 25% duty cycle, you're looking at 25% of the time for the whole period, the signal is actually on. Okay. So 75% of the time it's off. Okay. Unfortunately for us, this implementation of the signal that we have here cannot be used for that purpose. Okay. So instead, we'll stop the simulation and we'll move it to an Arduino unit. So we're using pin number 9 for in this case. And we're also moving this one to pin number 9. So we'll just make it a bit more orderly as possible. Change out a few values here and there. There. And we'll connect our ground line to this one, negative. Okay. So in this case, when we're using the code or the native code for Arduino, we need to set pin number 9 as output and we need to write in analog write. So if I want this one to be permanently on, I just basically write 255 and be done with it. So initially you see that and then it goes to the always on condition. Okay. If I want a 50% duty cycle, I have 255 and I get 127. So this is a 50% duty cycle. A 25% duty cycle would be 63. A 10% duty cycle would be 12.5% yung isa. So 255 times 0.1, which is 10%. 25 lang dapat to. So that will give us a value out of it, which is a 10% duty cycle. Now, for practice or in practical aspect, the utilization of PWM signals is primarily used for control structures. Just like it was originally used for controlling steam engines, we typically use them to control physical control structures like a DC servo motor. So in this case, if I want the motor to go to a 90 or 45-degree angle, I would set it to 127 and I would get that 45-degree angle. If I set it to 200, I get something above 90. So if I put it to 190, I should get a 90-degree angle out of this one. Okay. So if I wanted a value which is higher, I would set it to 235. So this is above 90-degree position. Okay. So around 125 degrees. Okay. So this is how we typically use PWM signals. Okay. For control systems for industrial machines, VFDs and step servo motors, AC servo motors use PWM signals to operate them. Okay. So a AC servo motor has two coils. The coil that makes it rotate towards the right and another coil that makes it rotate towards the left. So you need to apply a pulse signal of 10,000 counts in order to move that particular AC motor forward or reverse. Okay. So let's now proceed to an OpenPLC application. Okay. For the OpenPLC application, we don't really need to use anything but the D9 value. Again, let's go to explain the D9. D9 has a tilde attached to it as well as 10 and 11. And if we look at the documentation for OpenPLC, these are considered to be analog write or PWM signal pins. So by placing in an initial value of 0, I'm making sure that I don't get anything out of this pin. Okay. So here I have a ladder diagram that details that D2 is an input to D13. So D13 is QX03 and D2 is IX00 or 0.0. I've actually physically connected D9 towards D2 in front of me. Okay. We can try to see the transaction taking place. I've already included the program into the Arduino. When I do a Modbus connection towards my Uno. So you can see that uh, 4 has nothing going on. If I change this one to 999, kasi we have a 16-bit number that is attached to this one. In front of me, I'm seeing the LEDs basically turn on and off. Okay. So here, you can see this one turning on and off yung D2 natin. While 4, on the other hand, hasn't, ayun, it's actually changing now. So if I change this one to 10,000, okay, I'm still getting a readout of on and off. So I put it to 20,000. Okay. So you can see D13 is turning on and off, okay, in front of you. So if I put this to 30,000, I'm seeing a longer period of being on. If I put it to 60,000, it's basically always on. Okay. So if I put it to uh 5,000, I'll put an update. I can see it turning on and off very fast, but you cannot see it here in front of the ModScan 32 application that we're using. But it's actually working for our purpose. The only problem now is to try to find out what the actual values are. Okay. What value should there be in order to force the system to operate on a specific set of conditions in order to force the load in to function properly. Okay. So let's go back to Tinkercad in this case. So we now know that it can be used for a servo motor, but what is unclear is if we can use it for something else entirely different. Okay, which is the application of getting or using specific items for it. So I'm just resetting the system because the palette disappeared on me. Okay, so this is the palette. So I'm getting a DC motor. Okay, so I'm also getting a bridge circuit. This kind of always gets complicated whenever I try to do this one. So power 1, power 2. Power 2 is specifically meant for the motor itself, not the logic circuit. Okay. Power 1 is typically used by the controller. So it should be connected to Arduino. And then we have the connection of the ground points. Okay, ground and ground. So now we have the enable. Uh, I think this should be held high, not held low. Okay, so let's see. L293D datasheet. So it says here, active at high. Okay. I need a resistor in order to make sure that I don't break or I do not break my inputs. EN 1 and 2. And we'll connect this one to the power supply. So this is my input, this is my output. My output goes towards my positive terminal. And this input now goes towards my okay, my timing pulse. Oops, sorry. I forgot to place in the ground point. Okay. So you see here, it's now rotating at a specific value. Okay. So let's modify the code. Delay 2 seconds. 1 to 7. Or delay 4 seconds. So we can see the effect on a DC motor. Analog. Right. 963 at 25%. So at top speed, at half speed, at a quarter of the speed yung susunod. And then it goes back to full speed. Okay. When we change the PWM signal. So essentially you can use a PWM signal to also to control a DC motor. Okay. So we can add in 10%, which is 25. Half, quarter, and then 10%. So your motor has gone down in its speed. So you can easily do the same thing here by simply just going, I think 5,000 is, you have the calculator. 60,000 times 0.1, 0.00. 0.1, yeah, 10%, 6,000. So this is 10% of the signal only. The 30,000. This is half of the signal. 15,000 is 1/4 of the signal. So you can barely see it in the input, and then the output tries to play catch up. 75% would be 45,000. So on and so forth. So again, when we go back to the deployment circuit, you just basically play around with the value of D9, and that's it. This ladder diagram that I have here was done in order for the viewer to see what is actually happening to D13, since we ported in D9 towards D2 physically by a interconnection cable. Okay. So that's it. This is PWM signals for us. So again, when you have anything that tries to control a speed of the motor, you use a PWM signal. Okay, instead of having a timer mechanism attached to somewhere, just use a PWM signal. Okay, so let's do a stop for the video. Thank you for watching.